All right, the time is now 1:25 p.m. Eastern Time, so that concludes our break. We're going to resume our technical presentations, and we're going to start with Jason Stelly of Jacob Space Explorations Group, and he'll be talking to us about MAV prototyping with a cFS-based simulation. Jason.
All right, thank you. Yes, so I'm Jason Stelly, and my partner cohort in this was Derek Biglari. And yeah, we worked for Jacobs at Marshall Space Flight Center for NASA for the MAV project. Next. So MAV is part of the Mars Sample Return Campaign. It's a complex mission trying to return samples of Mars to Earth. And the MAV is the rocket that's going to launch the samples into orbit around Mars. So it's very short duration of active flight that we have to deal with. Next. And Stephanie went over some of this the other day, just for reference here. You know, we got the Mars 2020. I believe it's landing next week on the 18th. And we're the MAV, the Mars Ascent Vehicle there on the upper right there. So we're going to land with the SRL and the Fetch Rover. The Fetch Rover is going to pick up some samples, bring them to the MAV and put them in the orbiting sample container. And that's what we're going to put into orbit. And then the ERO comes by and picks that up and returns it to Earth. Okay. Next. Go ahead, next. Okay, and this is just a representation of what would basically look like for us to launch from Mars. So as we try to sim things, we try to keep in mind, you know, what it is that we're actually trying to do. So there's a nice picture of that. Next. Okay, so what's the flight plan actually look like? We've got the SRL there on the lower left. And that's going to toss us up with this vector launch system there, vertical egress controlled tip-off rate mechanism. And so it's going to throw us up, and then we're going to launch our first stage rocket. We're going to control with our TVCs and RCS and go, as they say, uphill. And then once we're done with our burn, we're going to do a little spin, separate, do some more spinning, fire the second stage solid rocket motor, and then do a D-spin, and then once that's done, do the release of the OS, and then the ERO would come and pick us up. So this is what we needed to sim, or what we need to sim going forward, and that's what we're trying to make work with the flight software. Okay, next. So as background to where we started with this, the software architecture and design decisions that needed to be made at the time, we had a number of software trade studies going, prototyping efforts that we were doing. We had some early GNC algorithms, and we needed to do some closed loop simulation with flight software and something else to be able to do our performance and constraints for the system under test. So we needed to do this quickly for the studies and the results that we were looking for. And we needed it to be, you know, an integrated test sort of situation, not just, you know, a unit test thing. And so we had looked at a number of simulations to make this happen. And we had a decent view of the layout, the lay of the land for what was needed. And so based on the team familiarity, the given capabilities that we had, the expected development speed for each of the environments and whatnot, we chose cFS as the base for our prototype simulation for physics and hardware components. And we'll see how that goes. Next. So what was needed? We needed an very early prototype simulation. Didn't have to be the final formal thing. Didn't have to have all the great fidelity that we would end up with. We just needed answers really quick. So that went into it. Also, the the payload, you know, our main goal was that the payload needed to reach at a given orbit, given, you know, altitude and angle of inclination for the orbit. And so the physics, the interface simulation, it needed to be separate from the flight software for a couple of different reasons. We had performance numbers that we're trying to look at. And so those things being separate, we could run them on different hardware items, different CPUs or different cores when we can. Of course, we're all working from home, so a lot of the work lately has been in virtual machines. So one of the modes we needed was a lockstep I/O mode that would allow a dropless mechanism. It would allow for potentially faster in real time, where we wouldn't have to worry about the flight software performance per se, and more understand its functionality, whether or not it's actually going to command the right things with the right inputs. And then we had another mode, it was a free running mode, where we can actually understand the performance and whether or not the flight software is going to get behind because of CPU or because of I/O issues. And so we had those two modes that we wanted to work with. So the simulation, you know, what do we need in simulation? We need the launch state. We need the navigation sensor systems like IMU, say. We needed forces and moments, the main engines, flight control systems, separation events, environment, so on, right? So considerations, you know, we needed the IMU to give some good data. It can be perfect at that point in the prototyping. We weren't too interested in, you know, dispersions and, you know, faulting it and giving bad data and all this other stuff. But it did have to have an accurate representation of the interface. So it had a reduced resolution from, you know, the near perfect nature of the SIM data. So there was some reduction in the resolution there, as well as some other slight contortions that we had to do to make the data rates happen and all that. So control systems, you know, they need good timing. They need forces and moments. So all the RCS, TVC, the solid rocket motor, all the different curves and natures that you know go into those things, the different functions that are involved there. All those things had to be considered, at least for a low fidelity sim that we were talking about. For a higher fidelity, you know, we potentially step up the mechanism, the method for simulating those components. So those things just had to be considered and weighed into the process. So at that stage, when we're doing early prototyping, this is before a lot of the work, before we even got requirements going, which was recently. So it was very early, and we were concerned more about if it's going to fly, not necessarily how well it's going to fly. With the hardware that we're looking at, you know, a flight computer, and we're looking at certain types of flight software and whatnot, and so we're just trying to understand, you know, whether it would be possible, not necessarily how well. Okay, next. Okay, so why create a cFS-based simulation? cFS provides a real-time capable architecture. It's got modular components that could be for emulation of physics or sim interfaces. You've got capability of doing ground system interfacing using CCSGS, and you could use different ground systems if you like. We were using the cFS Python ground system just because we only needed a handful of commands. You know, we didn't need 1,000 commands or anything to get running. So all we had to do is, you know, tell the sim to go and launch, and away we go. Okay, And another bonus there was the platform portability. We could run it on our VMs. We could run it on a piece of hardware in the lab. When we get on site, we could run those, and potentially other platforms that cFS supports. With the sim being cFS and the flight software being cFS, there's the common architecture there. There's code reuse. There's reduced training needs. So that was really good. The relatively simple design of MAV allowed for only a few interfaces, and the amount of data that we needed to send wasn't so extreme that we couldn't take some of those interfaces and combine them, reduce even more, and make a much more simpler design for testing these very early prototypes. So it wasn't necessarily flight-like in that way, but it was what we intended to do for prototyping. We needed something fast, as in timeline-wise, schedule-wise. We needed something that we can get our hands on and start running with and get our answers really quick. And the alternative would have required additional time to understand the code, configure, I/O interfaces, understand the mechanisms of the sim itself, how it was doing things. In one of the cases that we're looking at, one of the sims, we would have had to modify some very large, abstract, very heavy object-oriented code that was an in-house product, actually. And for us, looking at it, we estimated it would take us well beyond where we wanted to be for trying to get these answers. So that was clearly out of the picture for us at the time. Another thing that we looked at was it would take us time to learn certain new simulation architectures, such as like 42. We looked at it. It was pretty good, but we were concerned it lacked a few of the things that we needed, in particular to Mars environment, or say, we had to, model the vehicle and get all the aerodynamics correct and all that fun stuff. So getting all those things working in some of those other environments, for modeling sake, were a concern. So following that, we knew that we had expertise in-house. One of our previous tasking items that we had was to do a standalone flight software instance where it had the physics embedded. And so we could take that instance, throw it on a piece of a prototype flight computer and run that, and it would give us some of the answers, right? But it wasn't a separate thing. It wasn't allowing us to run and get true performance numbers or true I/O numbers. And so there was that. So, but we already had that physics, right? So we had that physics in hand, and we could use that going forward. So that was part of our logic in going this direction. Okay, next. So with that in mind, with the time, with the physics in hand, basically all we needed to do was stand up some apps. We had to stand up the simulation interface to do things like initialize with initial conditions, pause, resume, stop, do maybe some faults. We had the physics, so we just needed to get those into an app and stitch together the interfaces. Then we had the emulated components, the TVC, the RCS, the IMU, Pyro, whatnot. We just had to make apps for those, make interfaces defined for those, for the different connections that we're going to use, and define the commands and telemetry responses that we needed to do there. So those were the basic things we needed app-wise. We're going to use the SCH app, which will allow us to do simultaneous scheduling of the different components. So we took the I/O and said, okay, all the input we can run first, all simultaneously across multiple threads. And that worked out great for a multi-core machine, so that was good. And then we could run the physics and then do the output. Excuse me. The control and telemetry from the sim, we didn't use too much telemetry from the sim, but we could have. It was surely there if we wanted to. But for commanding, we just used the cFS ground station, the Python one, and set it up with a number of commands that we needed for commanding the sim and sending commands through our. Actually, we simulated a SRL component, so we shot commands through that SRL component to the flight software. So that was another set of commands that we sent through there. And one of the nice things about using the cFS was that we could potentially reuse products, metadata products, or tooling that we would use for the flight software as well as the sim. And of course, if we're running cFS, it could be run on a desktop, a server, or anywhere that cFS runs with enough CPU and I/O capabilities. So that was pretty good. Next. So this is our basic setup visualized here. We had some I/O using RS-422 between the hardware and the sim. We had a couple of different test setups for lockstep and free running. And in this early prototyping stage, we really didn't care about time synchronization techniques. We didn't do any GPS sync or anything. We don't have GPS on Mars, so that's really not a thing. So really just running these two components, free spin on each of the processors, let them skew and drift, and turned out that it handled it fine for what we were trying to get after. So on the left, we see the RTIMs that we were using on the flight computer. We see the cFS running inside that, our apps running in there, SCH, CITO, CFDP, IMU, TVC, Pyro, RCS, SRL, and the NAV app running the GNC from our GNC folks. On the right, we see our sim machine running on Linux, on Linux OS with the cFS-based sim using emulators for the SRL, RCS, Pyro, TVC, IMU, and we see the SCH app there. And then we have the CITO to do commands and telemetry to and from the sim, to the sim ground station there and on the control station. And we've got the physics driving the simulation for our truth state, which drives all the interfaces over to the flight software. And it also stores a CSV trajectory file. And Derek stood up a tool we call MAV 3D, which just takes our trash file and does a playback of it, or we can live stream into it and see the trajectory and propagate it. On the left there, we've got a debug console that allowed us to do the flight software loads and debugging directly on the flight computer. So that was our basic setup. Next slide. Okay, so the time to develop to do the basic physics model in cFS went very quick, given that we already had physics in hand from our earlier work. The integration with the other subsystems, for the RCS and TVC, we were able to pull that data in to provide modeling for those things, at least in a low fidelity way in that early part of the project. And the time to create those components was very quick. We probably got the I/O components done within a week or two. Just very simple command telemetry blocks to send through on each of those things, and then the models were very simple. And so we what we realized up front was that we're going to have a template, and that is going to just be a templated cFS app. And all we had to do then was swap out the command to telemetry blocks and write the model code, and off we go. We didn't have, it's not a SLS, it's not a space shuttle. Literally you saw the models that we did there. That's not an excessive, triple redundant system with, human spaceflight requirements and all that fun stuff. So very, very small number of models there. The initial integration time between the flight software and the sim was very quick. Most of the time was spent up front doing integrating the GNC IO parameters, just trying to understand what they wanted, what units they were, what size they were, whether or not, we're talking deltas or, averages or summations, whatnot, trying to figure out those things and get those things sorted out with the sim and generating those parameters correctly. That took a lot of time. So the flight software and the sim, we ended up testing in a Linux VM for the most part, and then tested eventually on the hardware. And after that initial few weeks of getting it stood up, we increased the fidelity throughout the project. Next. Performance-wise, doing the parallel triggering across the apps, it worked pretty good. This is a snapshot of the performance. We see it's pretty fairly steady there. It's got a little bit of fluctuations here and there, but as I say, we weren't syncing it to any kind of time signature, so it wasn't. It wasn't expected to be perfect, and it wasn't perfect, so it's fine. When we decide to get more fidelity and more formal in our sims, we'll start looking at the synchronization needs there. As we were going through our real-time performance testing with the sim and the flight software, we found some early issues with the configuration, and this has been directing our path forward. So it was really good effort to be able to get that prototype out there really quick and start getting some of those answers. With the physics as low as fidelity it was, is with the amount of math that we're using and with the modern processors, the physics was running really fast, and we were able to run it much faster in real time, which was really good for fast turnaround on development. The sim performance, we found that we chose some IO speeds that limited some of the performance for the fast and real time lockstep. If we had chosen some faster interfaces, we could have run much faster, I believe. So yeah, the lockstep was limited by the IO and also the flight software speed on the target hardware. Okay, next. Okay, so lessons learned. We enabled some rapid prototype integration of the flight software components. We allowed the rapid completion of a trade study. We got our prototyping and testing going pretty good, and we with this prototype sim, we were able to continue that testing, and we've got a formal simulation trade study in work that this will go into the bin and be compared against.
Just about out of time, Jason.
Okay. So we had a number of lessons learned there, and yeah, it was really good. Next. And yeah, so we'll continue to reassess our sim, make sure that it's the right answer for what we're going for. And we're considering doing some app templates potentially for the sim technique. That might be good to release at some point. And we'll continue to integrate our flight software and sim and try different scenarios. And I'll leave you with that.
All right. Thanks a lot, Jason. Great presentation. We do have a question from Klaas Zemke, and I recommend we transition that over to Slack. Thanks a lot.